Good afternoon, everybody. Chris here from RF Venue. Thank you for joining us for the fourth session in our ongoing weekly RF training and Q&A series. We have an exciting one today about creating a link budget for your wireless system. It's critically important both in the design phase and when you're actually deploying your system to kind of verify that everything's working the way you expected it to. So Don Boomer is going to lead us through this again this week. So if you have any questions, be sure to submit those. We will try to get to them at the end of the session within the time we have allotted. So without further ado, Don, take it away.
Thank you. Chris said exciting session. I don't know what that says about us as a community, but
no pressure.
If this is excitement, all right, it's going to be a rough ride. Okay, so today what we're going to talk about is a link budget. This is really helpful when you're putting together a system, so that is my system going to work? Is it going to cover this distance? What do I need to do? Do I need to change some components? It's going to give you a real solid basis for starting, and you can do this before you take everything out in the field. You could do this for every show you're going to do. You can do this for every install you're going to do. You can check your existing system and maybe learn how much headroom you have, how much stability you might have. So this is to quote Chris, this is a really exciting subject, and we're tailing on to a presentation that we got before that Jason Glass did, distributed antenna systems. We had to edit a little of that one because it was kind of running long on time. I'm kind of going to pick up that, so Jason's going to be helping me out here today. But I wanted to kind of explain this in simple terms, and then we'll show you how to get a real exacting design. So with our link budget, basically what we're going to do is we're going to add up all the pluses from all the gains, and then we're going to subtract all the losses, and we're going to see what we end up with, and then we're going to see if that's enough. So I assume you've got a wireless microphone or belt pack in mind. You're going to see typical power levels like this. Again, I must say everything that I'm saying here is very US centric. There are different frequencies that I know the rest of you guys around the world are operating on. A little different here in the US, little different power levels depending on where you go in the world. For example, in Japan, 10 milliwatts is the most power you can use. You have choices that typically look like this. In the US, 50 milliwatts is the maximum amount you can use without a license. So to use beyond that, you got to be a pro, get a license, which is a good thing to do if you can do it. But anyway, so you start out with a transmitter. And this is the power that it's rated at. It's not necessarily the power that comes out of the antenna. There's some tiny losses inside, but we'll get to those later. So you've got this transmitter, and now, somebody's going to hold it in their hand, or somebody's going to put it on a belt pack. And human body is an interesting thing. It both absorbs and reflects RF. But in this case, the losses, you're going to have some losses. So typical losses, about 8 dB if you're holding it in your hand, 20 to 40 on a belt pack. It depends on your body size. It definitely matters if it's touching skin. You don't want that to happen. You do need to insulate it. And actually a neat little trick for that, I don't know if I've mentioned this before, if you have belt packs, a neat little trick if you've got the little whip antenna hanging out the bottom is to take a piece of soda straw, just a plastic straw, and thread that antenna through that, tape it on, and then that's going to keep the antenna off your skin. It's also going to help keep the antenna straight, which is going to benefit you in the long run. Okay, so we've got our microphone, somebody's holding it or wearing it, and we lose a little for that. And now we have to transmit that through the air to our antenna. Well, we lose some power going through the air, and that's called free space path loss. It depends on frequency. The numbers that I picked here are typical sort of mid-band 550 megahertz-ish in the US. If you operate at a higher frequency, you're going to lose more. If you're up in the 700s, then your number is going to be a little higher. If you're at the lower end of that band, if you're down in the 470, 480, 490 T band down there, numbers going to be, you're not going to lose quite as much. We'll be able to put in exact numbers later when we get to Jason's calculator. But I just want you to be aware kind of the general kind of loss you're going to expect transmitting through air. So that's a loss. Now, there's also going to be another loss, and we talked about this before on our first webinar, Why Mics Drop Out. If you missed that one, it's on our website. Just go to rfvenue.com, scroll down to the bottom, and these webinars are all available to watch later. Anyway, so there's a thing called polarization loss, and that basically means you're going to lose a little bit of your power because the exact alignment of your transmitter's antenna isn't going to be perfect to your receiving antenna. It's going to be all over the place as people move. So we got to count a little bit of loss in for that. So I'm using 3 dB. It's a good figure. It could be a whole lot worse. So, but it almost is never going to be better than this. So we're going to add that. That's another loss. And then we come to our antenna. Now our antenna has some gain. These are typical amounts. We talked a little about spec sheets before when we talked about polars. So whatever your antenna is, I would suggest you go to your manufacturer's spec sheet. You're going to get maybe a slightly more exacting number than this, but these are kind of good ballpark numbers to just understand. So that antenna is going to boost the signal a little bit. We've lost a lot coming through the air. We've lost a little for body and for polarization errors. We're going to have a little gain back with our antenna. And now you've got to connect that antenna with a cable. Coax losses, again, this is sort of figured at 500 megahertz. Again, whatever wire you're using, you can go to the manufacturer's spec sheet and you're going to see the loss. Typically, they show the loss per 100 feet or per 100 meters. It's easy to calculate. But pay very close attention to the frequency that you're looking at, right? Because this wire loses a lot more in high frequencies and a lot less in low frequencies. So don't make the mistake when you go to that spec sheet and see that it's written for 200 megahertz. It's going to make your wire look a whole lot better than it's actually going to be in practice when you get there. So these are typical wires. RG58 is the little antenna wire that everybody's used for forever. I recommend you don't use that anymore. From this day forward, no longer buy RG58. RG8X is a much better choice. It's almost exactly the same size, pretty much is a straight replacement, but you can see that the loss in RG58 is 50% more than the loss in RG8X. Plus RG8X is 100% shielded, so that's going to help you avoid some other problems. You know, if you're running a long distance, you're going to need a bigger wire. I tend to use LMR 400. There are other numbers out there. You can go to pretty much any of the coax spec sheets and see what that is. But an awful lot of people in the pro sound business in the US, in the movie industry, they use LMR 400. So there's a lot of it around. It's very typical. I see this all over the place. So we're going to lose a little bit with our cable. So here we are so far in the path. And then of course that cable, unless you're plugging it straight into the receiver, you're plugging it into your distro or your multi-coupler. If it's an active unit like our Distro 4 or other brands, it's probably not going to have any loss. It's going to be somewhere from a unity to maybe a plus 3 dB, depending on a number of things, depending on frequency. But again, if you look on the spec sheets, you're going to get a number. Now, if you're using a passive, you know, you might be running into a passive splitter, in which case this is going to be a loss. But with an active splitter, it's usually neutral to maybe just a little bit more than neutral, slight amount of gain. So here's the path so far. And now, of course, we're going to need another usually short cable that's going to go out. So we got another loss. You know, if this is a foot or two, this isn't very much loss. A fraction of a dB for the cable itself, a little bit for the BNC connectors. We can get down to the end of the weeds and we'll figure all the tiny little bits later. But just sort of get a general practice or a general feeling, excuse me, for what's going on. There's not much loss here, but there is, you know, count a dB or so. And then we finally get to the end of the line. This is going to plug into our radio. So this is typically what a path looks like. There are some more things that you can consider, but these are the big chunks. So you kind of figure this out as you're going along, right? We've got gain in our microphone. We've got loss from holding it. We have loss as it travels through the air. We have loss because our antennas will never be in exactly the perfect spot unless you nail everything down. Then why would you use wireless if nothing's moving? That gets to be a problem when you start doing, microwave, but we're not there. Anyway, forget I said that. Then we had a cable that's going to connect it to our distro, a cable that's going to connect from our distro to our receivers. That's pretty much our path, right? So this is pretty straightforward. You can see where you have gain and where you have loss. So if we kind of plug some of these middle numbers back in with 30 dB transmit, let me interrupt myself. I should have said it on the first slide when I was back with transmitters. One of the neat things that a link budget is going to allow you to do is to understand how much power you have to have in your transmitter, right? Most mid and upper wireless systems now have adjustable transmit powers. It may say low, medium, high. It may give you numbers 10, 20, 30, 50, whatever it is. You'll almost always be better off using the lowest amount of power that you can use. So when we get done with this link budget, we can see that, oh, hey, we have enough power. Hey, what if I move it down to a lower power? Will I still have enough power? Or do I need to move it up to a high power? So this is going to answer that question for you, because if you can turn the power down, you are going to have less interference on your other mics, on your other in-ear monitors. It's going to be a good thing. You'll have more space for open channels. You'll have less intermodulation distortion. So always using the lowest power that works. You have to have enough to make it work, but you don't need any more than it takes to work. So back to the link budget. So I've selected 30 milliwatts for this transmitter. The power that the radio says it is the power, but it's got to get to its antenna, and the antenna inside the microphone itself may not be exactly perfect. So there's going to be a little loss inside that. And we'll dial that in a little more when we get to Jason's calculator. Human absorption, I just picked 20 dB that's a good belt pack number. If our transmitter is going to be 50 feet away from our antenna, we're going to lose something on the order of 51 dB in free space. If we have a paddle antenna out there, we're going to pick up 6 dB a gain. If we're running 50 feet of RG8 coax from our antenna into our distro, then we're going to lose 4 dB. And I added -3 at the bottom, figuring that the distro was at unity. We've got the output cable. We've got connector losses. That's just sort of a slop figure, but there's a little bit there. And we see that we end up with this simple link budget with -60 dB available to be plugged into your receiver. The question is that a good number or not? We have to look a little farther into. What you absolutely need, your receiver has a sensitivity. Here's some examples from Shure, Audio-Technica, Sennheiser. Every manufacturer has a spec for this. They're likely to use different numbers and a different way to express this sensitivity. But basically what the sensitivity means, this is the smallest signal that your radio can possibly tune in, get above the noise and work. I mean, you're right at the ragged edge. This is a very scary place to be. But this is the absolute drop dead minimum number under perfect no interference conditions that your radio could possibly work. You'll never be there, but there is a number. So you have to know that number. Your link budget always has to give you a number that's bigger than this. And I want to show you some things here. So if we go back to this, a couple of the biggest, easiest opportunities to make this better, or to find out, if you go the other way, you've got way too good a signal. Could you do it another way? Because that might be more convenient. In our free space path loss, and in our coax connecting our antenna into the rest of the system, I think are the two biggest opportunities to do something. So free space path loss, this is a logarithmic number, right? So if you cut a distance in half, you lose 6 dB. If you double a distance, you add 6 dB to the loss. We're getting numbers now, right? So moving around here, you pick up a whole bunch of power. The cable, likewise, is an easy place to make some changes. So again, your cable loss is very straightforward. If you cut the distance in half, you cut the loss in half. If you double the distance, you double the loss. It's just straight addition. Your free space loss, though, is logarithmic. For example, if your antenna currently is, it's your mixing position and it's 100 feet back from your stage, and this is your loss based on your mic and your frequencies, blah, blah, blah. If you were to move that antenna halfway up, you pick up 6 dB in signal strength. And if you were to move that antenna up onto the wing of your stage, you pick up 12 dB. That's a bunch of power that the air just soaks up. So there's a tremendous opportunity. Of course, now you have to run a longer cable and there's going to be more loss in the cable. But the cable losses are very small compared to the amount of benefit that you're going to pick up by moving that antenna much closer to your transmitter. So again, this is going to help you answer that question. When you get all done with this link budget, you'll see, oh, hey, I've got plenty available still if I put my antenna at the back of the house, or gee, I'm running out of room here. This is going to get kind of ragged and may become unstable. Maybe I better think about putting my antenna closer up to my performers. It's a good place, and that's one of the benefits of doing this link budget. You'll find it easy in Jason's calculator to go back and change a few values around and see how it impacts your system where you are, so you can make better decisions. Jason did this a couple of weeks ago, and I'm going to let him explain this.
So, like I said, this works on phones, tablets, and computers. Each one of these sections represents a portion of your signal path. Then we end up with a numerical results at the bottom, and it'll also, just for fun, it'll model your receive device metering. So we start at the top. The default here is 585 megahertz because that was the middle of the UHF TV band before the transition. The middle now, I believe, is 539. You would put this in the middle of the range that you expect to operate. In this case, let's say your microphones in. But in general, if you're just doing some general calculations, this is the middle of the current usable range of 430 to 608 megahertz. 539. So then we enter a representative transmitter output power. I'm thinking Axient Digital at normal power is 10 milliwatts. Your default system components impedance is 50 because most pro audio it's 50. I believe some micro systems operate at 75, but don't quote me on it. So since we're imagining we have a handheld microphone, we can ignore the specs for the transmitter patch cable, but you would need that if we were talking about an in-ear monitor transmitter. Transmit combiner, again, in-ear monitor. Transmit loss or gain, this is where a user can enter other losses and gains. Transmit antenna cable between the combiner and the antennas, but we can jump right to antennas and polarization. So the first thing we'll enter here is, let's say it's a CP beam with 12 dB. I'm sorry, this is the transmitter antenna. This is the whip sticking out of your microphone. I generally set these at 0 dB for mics. And I assume a 2-to-1 SWR, which is very good. And then you'll get a sub calculation total there. Now receiver antenna gain, let's say we're using a CP beam, 12 dB. We know from manufacturer specs, it's about 2.5 to 1, I believe, around that frequency. And then polarization alignment. This refers to the fact that we're using a linear antenna in our handheld. Now, Yes, they are actually little mini helicals in modern antennas, but after speaking to the manufacturers, I've discovered that they behave as linear polarized antennas. But our CP beam at the other end is a circular polarized antenna. So that's going to give us 3 dB of loss no matter what the relationship between those two antennas angles are. And now here's a biggie. Free space distance. At CMA Music Festival, I shoot for an 80-foot rock solid distance from my main antenna zone. So I'm going 80. These other parameters, absorption loss, this is when you have a body pack against skin, etc. It's self-explanatory otherwise. Multipath losses are going to be impossible to predict, but I allowed users to do it so that they could experiment. Our receive antenna cable at CMA Music Fest is 125 feet of Belden 9913 F7 low loss. I do want to calculate the connector's loss, and I deploy them with brand new condition. You have options there. Receive multicoupler, we're going to say unity gain. Receiver patch cables between our antenna splitter and our receivers, we'll say 2 feet of pretty standard Belden RG58 AU. There are better cables out there for that, but that's pretty basic. We do want to calculate connector loss. Other losses or gains are, again, an opportunity if you want to experiment with inserting attenuation or whatnot. So our numerical results. Go down here, and we see we have a received voltage of over 1,500 microvolts. I believe I may have made an error somewhere. That seems a little high. Let's see. Space distance. Nope, it's good. So we know that this system works in that zone on antenna A. It just so happens that almost all of my paths on my multi-zone on CMA Fest on the main stage, well, I should say on the main stage zone, including my in-ear monitors, are all close to identical. So this is a good rule of thumb to know that that system will work. But the other thing I want to point out here, this received voltage, I want to manipulate now this free space distance to try to get that number to 1,000. That's still too much. Let's say 120. Okay, 120 feet of free space between transmitter and receiver antenna gives me about 120 feet. I can now overlay the antenna pattern of the CP beam over a scale drawing of my CMA Fest main stage and scale that pattern till it matches 120 feet at longest gain, and then manipulate that around my drawing. So that's a really useful tool. Now, if you're looking at that drawing and it shows the pattern doesn't perfectly cover what you want to cover, keep in mind, that's your pretty sure it's going to be rock solid pattern. That doesn't mean that your signal is going to go away or not be usable outside that pattern. It is telling you best, you know, in your optimal setup, it's going to be good. So I hope that's helpful for you guys.
Thanks, Jason. So we'll put up here is the link to Jason's calculator. You can take a screenshot.
No, done. I actually, just to save it, because a bunch of people are asking me this, I've been posting the link in there. If you go to our blog, rfvenue.com/blog, and you go to that session, it's the second session, distributed antenna systems. It's linked there, and we'll put it in the blog for this one as well.
Yep. So
long URL.
Yeah. So you can jump over and use that. So this is a way to get a very complete link budget. Now, some of these things, as he pointed out, you don't have to put all of these things in there, but you won't get, of course, as accurate a link. And what Jason was doing there at the end was saying, well, my signal at 1500 millivolts is a whole lot stronger, microvolts is a whole lot stronger than I need. So how far can I stretch out? How far will that antenna still give me rock solid? So when you're designing a system, you have some play. Go back and change the distance until you run out of what you consider to be a good amount left. So I want to talk about this. So this is called RSSI. That's received signal strength. And it's expressed a number of ways, right? These are all the same number, right? We could measure in inches, feet, or yards, but it's all the same. It's just going to have a different designation on the end to tell you which system you're using. I like to look at the dB. Jason likes to look at the voltage. It's the same thing. It just depends how you're going to consider what comes next. What absolutely matters is your carrier to noise ratio. We went over this in the Why Microphones Drop Out series. So if we look at, I chopped off a little piece of a graph here, your receiver sensitivity is almost certainly down in that bottom solid green. Modern receivers are darn good. So you probably don't have to worry about that at all. But then there's a noise floor, and realize this is moving. That's not standing still. So where that floor actually is something you kind of eyeball however you feel comfortable in doing it. And if you were to look on a scanner, what this number that you see better be at least 20 dB stronger than that noise floor. Now, more is better. Obviously, in Jason's example here, that number, that spike should look a lot taller, and that's a good thing. It's rare, that you would have it so strong. It can get to a point, the upper limit, of course, is where it would saturate your radio. But unless you're, unless you put your mic on top of the receiving antenna, that's probably not going to happen. So you don't have to worry about it. But that's another reason that you do this link budget, because you may find out that you're really, really hot, and you could pad it down some. And actually padding it down actually improves your sensitivity down on the bottom, but that's probably a little more than we need to get into at this time. So there's one other thing that kind of went by quickly on Jason's calculator that you may have a question about. There's a thing called a Fornells Own. And what this means is, this is the way that your power spreads out from your transmitter. It blooms out into this Fornells Own. You can add this in. Actually, Jason's calculator is going to show you what this is for your specific system. So it's handy when you look around at your antenna placement. That's really what we're getting back to with this. So you'll see there's a first, second, and third Fornells Own. Basically what this means is that if you have something that is intruding past that first Fornells Own, the reflection off that piece is going to end up in your antenna out of phase. It's going to pull your power down. If it reflects off the second Fornells Own, so in this example, there's a tall building. This gets to be really, really, really important when you're doing really long transmission. And with wireless mics, we're generally talking about 50 feet or 100 feet, or something along like that. So this isn't quite as critical, but I want you to just understand this is a factor in figuring out how things are going to work. So the reason I want to point this out, we talked about it before when we talked about line of sight. So this is an approximation of the first Fornells Own. And what we're saying is there's nothing sticking up in there. Now, if we were to lower that antenna so the top of people's heads actually stuck up inside that yellow ring, the reflections off their head would come into your antenna out of phase. People don't reflect a lot, but like if that were the floor, that's why looking at the receiver in the red on the bottom, you are definitely in the Fornells Own, because the floor is going to bounce up, and everything that bounces off the floor is going to be out of phase into that radio. Likewise, if you had your antenna so close to the ceiling, then the ceiling is going to be inside that first order Fornells Own. So just in really big rough numbers, if this distance represented 100 feet, the Fornells Own, and it changes with frequency, but somewhere in the mid-band UHF is basically going to have a radius of about 7 feet. That's why we want you to get antennas up over head height, but they need to be a little higher than that because we don't want any bad reflections. We don't want to lose any more power just because we put our antenna 2 feet too low. You know, there's an opportunity here to see, and using Jason's calculator, one of the drop downs is going to tell you the Fornells Own for your system with all the stuff that you've typed in there. So that gives you one more place by working smarter. That's what we're trying to do. We're trying to work smart here. We're trying to eliminate everything that might get in our way that we can fix for free or we can fix for low cost. And this is just one more thing you can consider.
Yeah, there were a couple of questions about, and I was sort of thinking about this, is, verifying link budget, or like, the range of your link budget, what's like an acceptable outcome. So like, let's say I'm doing a, rough design for a system, not in the venue, just doing calculation like we did there in terms of which antennas, cable type, etc. When you're actually deploying the system, are there any specific techniques, with spectrum analysis or checking different sections of the link to kind of see where you are and gauge whether, the quote unquote real world is going to be consistent with what you came up with,
right,
back at the office?
Right. Well, so, if you measure you can avoid doing this. Probably a lot of you have never even considered a link budget and your system's working. Okay, it is. But this is going to give you a much better idea of where your limits are. So again, what we're back to here, the thing that you have to shoot for is that you end up with a number that, and it depends how your scanner is set. You have to end up at least 20 dB above your noise floor. So if you use our Vantage program, you can set a threshold. So taking one of these orange lines that I've got at the bottom there, you can set that, you can drag it up and down. And so I like to set that threshold 20 or 25 dB above my noise floor. And as long as my signal from the little skinny lines, the signal from a radio transmitter there is above that line, I'm pretty good. I don't have to worry about it much because everything's changing every second, right? People are moving with the microphones. People are moving their hands on the microphone. They're turning their back to the antenna. Realize this is not a one and done thing. This is constantly changing. So, whatever your level of ease is, and maybe that has to do with how much there's somebody there to deal with something should something go wrong. If there's going to be nobody there to deal with this, if you're an installer and you're putting in a system and at a school or something, and you got the boys vice principal in charge of this, well, I'm guessing he's probably not a radio expert. You're going to want to set that to higher. You want to know, that you have more than 20 dB of carrier to noise ratio. But that's the goal. As long as you end up with something, this is arbitrary. You set it wherever you want, but 20 is getting right to the edge of where, when somebody turns around, they could go off the air. So you want to end up, when you're done, and you're looking at Jason's here, with a number that's bigger by 20 dB. So in this case, let's see, putting my glasses on, this case, the top of that is at minus 82. You can see on Jason's over here, it's minus 46. So it's way higher. In fact, it's off the scale. It's so much higher than that. So what you're shooting for when you're all done, of course, now when you're doing your link budget, you don't know what your noise floor is, right? If you've never been to the venue, hopefully it's no higher than minus 80. Just depends how much local interference you have. So if you're kind of figuring that it's minus 80, so if you're at minus 60, you've got your 20, right? Now, if the noise floor is worse than that, that's not going to work there. And it changes. I think on one of our blogs, we took one of the RF Explorers, and your noise floor gets worse as you go up, right? So if you're working on the 27th floor, you've got more noise than if you're working on the ground floor, probably. We had one, we were testing a system in Boston there, and we were up on the 13th floor or something, and the noise floor was like minus 60. That's horrendous. That'd be a tough spot. But anyway, that's what you're shooting for.
Yeah, it's interesting thinking about this, you know, when in the context of ambient noise, right?
Mm-hmm.
So if, you know, you assume that you have, you know, tons of room from a noise standpoint, and then you show up and, like you said, you're maybe on the 30th floor of a building in a, you know, busy downtown area next to a ton of TV transmitters, and it's, you know, the calculators, you know, kind of does not help. And it's almost like you have to think in reverse, where you manipulate the free, the path loss number by bringing the transmitters closer to the antenna, maybe something like one of the RFNU spotlight antennas, which is -1 of gain. You know, it's actually a minus figure going into your link budget, but you're compensating for that by almost eliminating the free path loss number, right? Because you've got that proximity to the antenna that's going to reduce all of the surrounding noise and ultimately get you to the carrier to noise ratio, signal to noise ratio that you need.
Yeah, I mean, if you're doing a party on the 47th floor, you know, patio or something, the reason, I mean, a big reason anyway, when you're up higher off the ground like that, you're more in the sight of TV stations. Easier for stuff to get to. You're not getting any shadowing from buildings or others. So it's just something to know. It's harder, generally speaking, to work up high than to work down low.
Couple of questions about the ever popular LED wall scenario. If you knew that a set or a stage design was going to have LED walls, I wonder, could you almost factor that into the link budget and almost penalize the starting point? Because you could assume maybe that you're going to have some kind of, you know, pretty broad interference from the LED wall. So you'd want to like have an even better target. You see what I'm saying?
Yeah, so it doesn't, I mean, obviously this is a consideration we need to have to make our system work. It doesn't figure into the link budget, but what you need to know is that you're going to be working in a much more harsh environment. So that number, back to Jason's number, was at -46, you know, and my number was at -60. So his number is going to work in a much more rugged environment than mine is. So you have to get a little idea about that. LED walls, you know, it's getting better. It's getting, you know, newer FCC certified LED walls are much better than the inexpensive older generation imported LED walls that really didn't have any shielding in them. They didn't care. They just wanted the video to be up, and that's fine. You can actually, with a scanner, I mean, if that's what you're trying to get past, you can actually scan and see. So video walls kind of have nulls, right? So what you want to do, if you have a scanner and you want to see what the video wall is, you want to ask the guy to fire up that wall and make the screen white, right? That's the worst condition, or at least, you know, be running active video, but white's the best. And what you're going to find is more or less there's nulls kind of at the 45s, right? So kind of at one, if you were looking at a clock, kind of at 1:30, what is that going to give you? 4:30, 8:30, and 10:30. Those spots will probably have lower interference than the other spots. So if you can put your antennas there, you're likely to pick up some free advantage. There's other things you have to do to video walls. That's maybe a different topic that we'll get to, but it doesn't really figure into the link budget, but just know you're going to need a better system if you're dealing with that, so that your number is going to have to be, you know, that's why Jason picks, you know, 1,000 microvolts, because like he said, that's going to be rock solid. And this is a guy that's always working with a 100-foot video wall behind him, you know, because he's doing massive events all the time. So when that's what you're doing, you need a higher level of reliability than if this is in, you know, the school cafeteria, and maybe they've got 1 or 2 screens up, you know, that aren't very big. So it just depends.
A couple of questions about antenna placement as it relates to the Fresnel effect and you know, that slide we were looking at previously. There was one question using a D-fin, diversity fin antenna, approximately 100 feet from stage with the control booth in a 2nd floor balcony. How far below an acoustic tile ceiling would you recommend mounting the antenna to account for the Fresnel effect?
Well, it's going to tell you exactly if you plug all the numbers into Jason's calculator. Somewhere on that sheet, it tells you the size and the radius of your Fornells Own. So you want to be, you need to mount the antenna low enough so that the first Fornells Own is a bit lower than the ceiling. The second Fornells Own, if it bounces off the second Fornells Own, it comes back in phase, right? This is all wavelength, right? There's definite sizes to this, and it depends on the frequency of your mic, and it depends on the distance between the two. You can calculate this out. That's why we're using this calculator. That's why we're showing you this today. This is going to tell you exactly where your antenna needs to be, depending on the mics you're using, the frequencies you're using, all that. You're going to get a hard number, right? I mean, like I said, I'm guessing, you know, at roughly 100 feet in roughly mid-band, the Fornells Own is about, the radius about 7 feet from center line, right? So in that case, you want to be 7 feet below the ceiling. You know, I mean, if you can't, you can't, but now you've got just other problems to worry about. Now you're going to need a stronger signal because you're losing some of your signal because of that. That's why we're doing this link budget. So you get a handle on potential problems before you install all your stuff. You don't have to take it down and remount it and get the cherry picker back out and zoom back up into the air. Better to know about that beforehand. So this is how you can figure that out. It's a really easy tool. Jason has a lot of numbers in there, and you can dial it in. I mean, did you see when you figure in BNC connectors, are they brand new, or are they sort of used, or are they very used? I mean, there's a lot of detail. He's got every brand of coax cable in there. So you don't have to figure it out. You don't have to go find spec sheets. Just drop down on the list and it's probably there. It's a really neat tool. I use it all the time. I found it about a year ago. It just makes it easy. I mean, this looks like a lot of math, but it's not. You're just entering the numbers in. And, you know, you're filling in your name and address, and it's going to tell you the answer at the bottom. The whole purpose of this is just to try to get you to the spot where you're comfortable knowing that, hey, if I do this, it's going to make a big change for the good or a big change for the bad. You know, we got calculators that'll give you stuff out to decimal points.
There were a couple of questions about the manufacturer's specs, the sensitivity. If you want to jump back to that slide real quick.
Yeah. So
this is
like
usually,
I said, you know,
this is usually not an area where people are looking, and so I just thought it might bear a little
yeah.
More attention.
So frankly, everything now is so good. I mean, if you spent $500 for a wireless, you got a good number. You know, I mean, if you've got $100 wireless mics, good luck. And if you got really old mics, good luck. They're going to have to change them. These all say the same thing, but none of them look the same. I'm not saying these are all identical, but I'm saying, so what this tells you is, this is telling you a level, a voltage level, a power level that needs to come into the input in order for the radio to push the signal above whatever they consider the noise of their own radio. Because if it's buried in the noise, you know, you can't hear it. Even if you're talking and you're testing your system, you're running pink noise in the auditorium, you can't talk over that. So this is telling you what level you need to get what they consider an effective amount of quieting, kind of. You know, manufacturers got different ways of expressing this, and you have to understand these numbers if you really want to dig in deep. But it's a little like power ratings for power amplifiers. You know, we got RMS, we got instantaneous peak, program power, we got 85,000 ways to say the same thing. And you have to, you know, if you're making a comparison from brand A to brand B, you're going to have to flip one of these so that you're speaking apples to apples, if you really want to know. The bottom line here is the lower this number is, the smaller this number. So if we take the Shure number that's minus 98, if they also had a radio that was minus 108, that's a more sensitive radio than minus 98, right? If we want to take the the Audio-Technica one there, 20 dB microvolts, if that were a smaller number, that would be a more sensitive radio. Radios are pretty darn good anymore, so you don't have to worry a lot about this because this number is almost always guaranteed. I don't know how you could ever have it not be considerably lower than whatever the noise floor is going to be wherever you are. So that's the one that really matters. I mean, this is an absolute cutoff. It has to be this or it doesn't work, but it's always going to be better than this. I mean, this is, well, I guess, you know, this is going to tell you it's not going to pick up from 20 miles away, I guess, because your signals are going to be that strong. But in the real world with what we're doing, it's pretty much guaranteed it's going to be satisfactory to some level. But, you know, that's not as common a use for wireless mics. So I don't worry about this too much, but I just wanted you to know this is the absolute cutoff, right? There's no, if you're less than this, it's not working, guaranteed.
Jason was just texting me saying, with respect to LED noise in the calculator, that's a good scenario where you'd want to put in some attenuation to both the system and into the calculator to reduce both the carrier signal level and the noise level to determine if you still have enough amplitude on the carrier.
Yeah, I guess we'll have to get into that. So this is something that's non-intuitive, right? So because it feels like if you're driving your car down the street and you want to slow your car down, you know, you can take your foot off the gas or you could drag an anchor behind your car. Dragging an anchor behind your car kind of seems like, why would I do that? So putting a pad, wait a minute, I just bought this antenna and I bought all this good gear and I'm going to squish some of the level. It seems backwards, but it's actually a good thing depending on the numbers, because as you lower the level, you are lowering the noise floor. And that gets back into that sensitivity thing. Sometimes you'll see it called SYNAD, which is signal noise and distortion. So if you can lower the noise, it makes that sensitivity better.
And I think last thing to touch on, again, if you jump back to the slide that showed the two kind of primary drivers of the link budget, the transmit power setting and path loss.
Okay, let's see, going backwards.
I was just thinking like a sort of a final takeaway, or it wasn't transmit power, but I think an important takeaway here, other than all the detail that you can add in, the biggest drivers of this number that you can typically control are the transmit power on your wireless mic, and then that free space path loss number, distance, right, between receive antenna and transmitter. So, you know, that minus 51 number would look a lot different if, you know, you were at 25 feet or you had a near field antenna, or, you know, you had a lower power output setting on your transmitter, but you've got a more localized reception area. And so I'm just making more of a comment. I don't know if you have anything to add to that, but if you had to sort of focus on two areas to really experiment with to see if you can get the link budget, you know, right in the sweet spot, see if you can do it with the lowest power possible on your transmitter, which, you know, has other side effects like extending battery life.
Right. Well, that's what's so great about the calculator, is it allows you to, hey, well, I wonder what would happen if I did this. Well, plug it in and see. Does it make a big difference? Does it make a little difference? Because obviously, if it makes a little difference but costs a lot of money, you might want to think about something else. You know, am I better off? Well, let's see. What we kind of skipped here was one thing that might happen because of that cable loss. If that was a really long cable and I didn't get a satisfactory number at the bottom, it's like, do I need to add a line amp in there?
Right.
So it depends. If it's a kind of bad number, I mean, what we would prefer you to do probably is spend that money for better cable, better coax, right?
Right.
But there's a place where that runs out, and you simply have to boost it to make up for the loss in the coax. This is where it's going to tell you, you know, so if you're laying out a system and you're going to run stuff all over a hotel, this is going to tell you, is this cable going to work or is this cable not going to work when you figure it in with the other things? Or if you absolutely have to use this cable, then what else do I have to adjust? Do I need a stronger transmitter? Do I need, you know, to change my path loss? What do I need to do? So it just gives you a bunch of places to adjust. You know, do you need a little more salt? Do you need a little more sugar? Do you need a little more pepper? You can kind of see beforehand, you know, so you don't make the stew that you can't eat at the end. You can avoid that step by doing the calculator. And so, like I said, you know, these are the important factors to get in there. There's a lot more little detail that you can get into, and as your application becomes more and more mission critical, you're going to add more and more of those things in. You know, I mean, some things that we didn't consider in here, and I guess maybe that's the next topic. We'll talk about coax a bit more, but this is considering that your coax cable is actually working correctly. If your coax cable's got, you know, bends and kinks in it, it's not going to give you this number, right? You're going to have to adjust for that. And actually, I believe you can specify the quality of cable, you know, new cable, used cable, that in Jason's calculator. So, but
there's a couple people asking about, you know, going back to the point about RG58, why we kind of steer people away from that these days. Number one is the loss, and number two is they're rarely shielded very well, and so there's some other downsides to using it. And for, you know, comparable cost or slightly more, you can get a much better quality cable in something like, you know, the RF Venue RG8X coax is, you know, double shielded, you know, super quality, low loss cable. I mean, it's not going to drive you nuts to work with it, right? Like a stiff, you know, LMR cable is great. It's super low loss, but, you know, if you got to go a long distance, I mean, good luck wrangling it.
Right. If you're yeah, RG8, right? The big cable, you know, that's as big around as your thumb.
Right.
And if you're running that 300 feet and you can't be splicing this together. Oh, there's another thing you could put in Jason's calculator. If you're splicing together stuff, there's a spot in there you can say, oh, I'm putting two 25-foot coaxes together to make a 50. You can make that because you're going to get some additional loss, and it may be okay, but this is going to tell you if it's okay or not. But anyway, when you're working with a big piece of RG8, I mean, the reason you're working with that is because you got to go a long way and you're really not wanting any loss. Well, that is a big, heavy piece of wire, 300 feet of that, and it's stiff as rebar. So it's not fun to roll up. You know, it's going to take a few guys to manipulate that piece of wire. Not much you can do about that, but this is going to tell you whether you need that or not.
Yep.
I mean, this figure, it goes up LMR 600, you know. I mean, that's that's some serious stuff. You know, by the time you get to that level, then we can start looking at running RF over fiber, which is you know, fiber is easy. You know, 100 meters of fiber weighs a pound. I can hold it up with my finger. 100 meters of, you know, of LMR 600 or RG8 is, you know, it's time to go get a forklift. You know, so especially if you want to pull that through a ceiling or something, that's a tough job.
Great. Well, looks like we nailed the hour on the dot there, Don. So why don't we wrap up there? Thank you, everyone, for joining us and all the great questions. I will try to follow up with as many of these as we can. For more info, be sure to head over to the RFNU blog, rfnu.com/blog, or get in touch with us directly. And we will see you next week, same time. Topic TBD. We have a couple options still in front of us, potential guest panelists. So we'll be sure to keep you posted on that for next Thursday. So thanks again.
I should say also, so when you go to these sessions, there's a spot at the bottom to ask questions, and we will be posting this webinar probably by Monday. Please tell us what would you like to hear about? What topics are important to you?
Yeah.
All this stuff is interconnected. Eventually, we'd get to session 50 and you'll have an awful lot of pieces, and 50 refers to 30 refers to 2, so all these things that we've talked about, they're all interconnected. But what's important to you? What is it that you want to know? And we'd be happy to take a look at that, because if you want to know it, probably somebody else does too. So,
exactly.
So let us know, ask a question at the bottom of any of these, if it's related to one of these or any place else, just send us that, and so we can plan for future webinars.
Perfect. All right. Thanks so much, everyone.
Thanks, guys.